Let's get going here. Okay, Chemistry 3101. This is approximately where we left off last class. It says predict the major and minor products for each of the following E2 reactions. So they tell us right away that we're dealing with elimination reactions, and these are bimolecular reactions. They're not asking for mechanisms here, but in the first one you see that we have an alpha carbon here, we have a beta carbon here, and we have another beta carbon here. And the reason I labeled these two beta carbons differently is because they have different types of beta protons, don't they? Now I could have labeled this carbon as a beta carbon, but the two carbons that I've labeled in red are identical to one another. So if I was to pull off this proton, that's a beta proton, and this is a beta proton. Well, sodium methoxide is an unhindered base. So this is an unhindered base, and therefore it's going to produce the more stable alkene, which is going to result from the abstraction of the proton in red, because we're going to end up with a tri-substituted alkene as opposed to a di-substituted alkene. Now we could draw the mechanism for that reaction. I'll just draw a negative charge here on my ethoxide. I'll remove the proton, form the double bond like that, and there's the loss of leaving group, and I would end up with this product, which is a tri-substituted alkene, which would be my major product. If I was to pull off the proton in blue, and I'm not going to put in the mechanism for that one, but if I was to pull off that proton that's labeled in blue or drawn in blue, I would end up with this alkene, which is only di-substituted. So this would be the minor product. Since the double bond is coming off of a ring, we call that sometimes an exocyclic double bond. Okay, if I move on to the next one, I have potassium T-butoxide. I have that in both of these here. And remember, the requirement is that if we have a leaving group on a ring, a cyclohexane ring, that it has to be anti-periplanar to a beta proton. So I have a beta proton here. I'll draw it going down like this. And I also have a two beta protons on this carbon, but I'm just going to draw the one that's pointing down. The reason why I'm only drawing the ones that are pointing down or the one that's pointing down in red, and of course the only one that's on the blue one, which is pointing down, is because if this bromine is up and axial, that would mean that both of these protons are down and axial, right? Remember that up and down alternate? If we have up axial, we have down axial, up axial, down axial. So again, in order for the beta hydrogens in the bromine, the leaving group, to be anti-periplanar, the requirement is met here, and it's also met here. So that means I could abstract either of those protons, okay? Either of those protons, the one that I have highlighted in red or the one I have highlighted in blue, could be anti-periplanar to that bromine. So if I abstract the one that's in red, I would end up with this as my product here. So I'll end up with this guy here, like that, okay? And if I abstract the one that's in blue, I would end up with this. So I'm going to eliminate that stereocenter, like that. Could anybody tell me which one of these would be the major product? Would it be the one in red or the one in blue? Well, if we look at the substitution of these, you can see that this one is more substituted, right? This is a tri-substituted alkene, okay? Whereas this one here is only a di-substituted alkene, all right? So I would presume that the one in blue is going to be the major product in this case. All right, let's move on to section 7.9 in the interest of time and talk about SN1 and E1 reactions, which are unimolecular reactions. So if we consider the following reaction where substitution and elimination products are formed, when we just take this tertiary alkyl halide, this guy right here, where's my pen? Come on, there we go. If we take this tertiary alkyl halide and we just dissolve it in some ethanol, it's kind of interesting, just throw it in ethanol, we get two products. We get a substitution product and we get an elimination product. Now, this is a tertiary alkyl halide. We know that this is not going to be an SN2 reaction, right? SN2 reactions are going to work on things that are primary or secondary or methyl halides. Whereas we have our reagent being ethanol. That's not a strong base, and it's not a strong nucleophile either. So this doesn't add up to be an SN2 or an E2 reaction. Again, it turns out that the formation of these two products follows first order kinetics. So we know that this is a unimolecular reaction, which we could write that the rate is going to be equal to the rate constant only times the concentration of the substrate. That's the only concentration that's going to affect our reaction rate. Therefore, again, this is a first order reaction. Going back to general chemistry 2 on that one. Well, the first step for both of these reactions, whether it's a substitution or elimination reaction, is the same. First step is the same no matter what, whether we're doing the SN1 or the E1 reaction. The first step is ionization. Now, the ionization is simply the loss of a leaving group, right? When we lose that bromine, we end up with an ion, right? We end up with a carbocation intermediate. And then once we've produced that carbocation, it can undergo a substitution or an elimination reaction depending on how it reacts with the ethanol. So again, first step for that tertiary alkyl halide in that ethanol is just the loss of leaving group. You form a carbocation, and that carbocation can react. Well, let's take a look at the SN1 reaction first, okay, the full mechanism. So the first step is the loss of leaving group. Nothing new there. But the second step is going to be nucleophilic attack by the ethanol. Now, ethanol is not a strong nucleophile. It's a weak nucleophile. However, you can see that this is going to be a really good electrophile because it's got a positive charge on it. Then we form this intermediate here. Okay, this is called an oxonium. Oxonium ion, okay, where we have this positive charge on our oxygen here. And then another molecule of ethanol can come in and abstract the proton. So we do a proton transfer here in order to produce that ether, the substitution product. Okay, now again, it says here the entire mechanism of this reaction is 3 steps, but the last step is just a proton transfer. Okay, we have a special name for this type of SN1 reaction. Since all you did was throw this tertiary alkyl halide in ethanol, we call this a solvolysis reaction, right? Because the nucleophile also acts as the solvent. All right, let's take a look at what the reaction coordinate diagram looks like for the SN1 reaction. And there's something that I want you to memorize here, okay? And the reason why is because it's really important, and I've seen it come up on the ACS final exam. Now, if we look at the reaction coordinate diagram, it's here, you see we have the loss of leaving group, then we have the nucleophilic attack, and then of course the proton transfer in this case, okay? But I want you to have memorized what the rate determining step is, right? The step that determines how fast the reaction occurs. And that is the formation of the carbocation, okay? So this first step right here to produce the carbocation, that is the rate determining step, okay? You see it's the one with the highest activation energy, and therefore it makes sense, right? Because activation energy is related to the rate of reaction, okay? So again, the formation of the carbocation is going to be the rate determining step. That is important that you memorize that, okay? Memorize rate determining step is going to be the formation of the carbocation intermediate. Let's talk about those kinetics again. Now, I asked you some questions about kinetics of an SN2 reaction in the last lecture. We went over that a little bit. But since the formation of that carbocation only requires that ionization of the substrate only, right? It's got nothing to do with collisions between the substrate and the nucleophile, the solvent. Okay, it's got nothing to do with that at all. Okay, since the formation of that carbocation only depends on the ionization, the rate of its formation is going to follow first order kinetics, right? So you've got to understand that an SN2 reaction follows second order kinetics, and then an SN1 reaction follows first order kinetics. It's going to be really important that you're able to, that you understand that, because it's going to come up again and again in organic chemistry. All right, so SN1, what does it stand for? Substitution, nucleophilic, and then the 1 stands for unimolecular. All right, so it's pretty easy to remember once you've got, you know, SN1 and SN2 down pat. It's pretty easy after that. All right. Again, the substitution reaction, And we're talking about an SN1 mechanism. It's covered up by my pencils here. But anyhow, the substitution reaction occurs stepwise. We form the carbocation intermediate. Remember that this is the rate determining step, right? You notice that it's in equilibrium, okay? And then we get a nucleophilic attack like that. Now, if the nucleophile is a neutral species, like ethanol, like the alcohol ethanol, then you have to have a proton transfer at the end, but that's not always going to be the case. All right, well, let's talk about E1. We just spent some time talking about SN1, but we said, hey, if you take that tertiary alkyl halide, so this is called tert-butyl bromide, but if you take that tertiary alkyl halide and you put it in ethanol, not only do you produce the ether, right, the substitution product, but we also produce an elimination product, which you can probably, I'm sure you all figured out what the mechanism is, right? The solvent in this case is behaving as a base, and it abstracts a beta hydrogen, right? We have our alpha carbon here, we have a beta carbon here, so this is a beta hydrogen. They've only drawn in one just to show that one proton that's being abstracted. But again, here the ethanol is acting as a base, right? It goes back to Bronsted acid-base theory. What's a Bronsted base? A proton acceptor. There we go. And we end up with an alkene. So like an SN1 reaction, the E1 mechanism is unimolecular. It follows the exact same kinetics that we saw in the last reaction. What else? The rate of the E1 is the same as the SN1. So it's an elimination reaction. It's unimolecular, right? They both share the same rate determining step, which was the formation of the carbocation. What's cool about this is the reaction rather that we just looked at, we ended up with this alkene as a possible product, and we also ended up with this guy as a product. Now, if you look at the functional groups of these compounds, here we have an alkene, right? Not a big stretch there. And this is an ether. Okay, you heard me say the word ether, and if you're wondering, what do you mean by ether? Well, this is an ether right here. This is where organic chemistry gets a lot more fun than a lot of the content that we've looked at so far in this class, right? Because now we're looking at making compounds with new functional groups. And when we see a functional group in a compound, what you're going to realize or what you're going to learn in this class is that eventually you'll be able to look at a functional group and say, hey, I've got an alkene. I could make an alcohol from that, or I could make a dibromide from that. Anyhow, we're going to learn all kinds of different reactions with all kinds of different functional groups. So this is kind of the very beginning of that. Now, there's some interesting rearrangements that can occur in SN1, E1 reactions, and that's because they proceed through a carbocation intermediate. We talked about hydride shifts and methyl shifts, right, when we saw carbocations earlier on in the class. So if you were to take this secondary alkyl bromide here and put that in water, so again, this is just a solvolysis reaction, not only can we get the SN1 product that's shown here, right, which occurs just after the law, just the plain old loss of a leaving group, we would form the carbocation, water comes in, we get a proton transfer, and we would end up with this product. But also, when you form the carbocation intermediate, and I'll draw it here. So when you form this carbocation intermediate, you can imagine that you could also get a hydride shift, right? There's no reason why you couldn't get this hydride shift occurring to produce a more stable carbocation. So we see two different SN1 products, and we also, of course, get some elimination products. Here's another example. This one is a hydride shift, right? This one is the result of a hydride. I guess it's written here on my slide already. Where am I? There we go. So this one's the result of a hydride shift, but we could have the same thing occurring with a methide shift. Remember I told you earlier on that a methyl shift is sometimes called a methide shift. Anyhow, it would be the exact same thing here, right? We could shift one of those, son of a gun, Apple pencils, acting weird. Anyhow, there we go. We could have a methide shift and produce a more stable carbocation. And then, of course, water could come in and we do a proton transfer. So these are the kind of things that an organic chemist has to stay on their toes. This is a reason why an organic chemist has to stay on her or his toes all the time and always be on the lookout for these kinds of rearrangements. So when the primary substrate is reacted under solvolysis, only the product resulting from rearrangement is observed. Well, this is something new. A primary substrate. Now, we generally don't think of primary carbocations because they're so unstable. So this is a very specific or isolated case where we have a primary alkyl bromide, but we end up doing a solvolysis reaction, right? Water isn't a strong base, it's not a strong nucleophile, but we do get a reaction where we substitute the bromine for a hydroxyl. Now, the first step is not going to be simply a loss of leaving group like that, because then you would produce a primary carbocation. Now, I think it's drawn in our textbook, but this is not going to be stable. Okay, it's not going to form. And so not only do you get the loss of the leaving group, but you also get the methyl shift occurring at the exact same time. So again, this is a very special case where we get loss of leaving group and the methyl shift occurring at the same time to produce, in this case, a tertiary carbocation, which is stable. Then we get our nucleophilic attack and proton transfer. Again, this is a very specific case, but you can see why organic chemistry is logical, right? It makes sense, but it's the kind of thing where you have to be thinking about all the different possibilities that could occur at all times. Now, how would a solvent affect an SN1 or an E1 reaction? So far, we've looked at two cases. We looked at an SN1 reaction that occurred in ethanol. That was the first example. And then we just saw one in the last slide. They had water as the solvent. So you can probably guess that SN1 and E1 reactions occur best in a polar Protic solvent. And we discussed what polar Protic solvents are and polar aprotic solvents are, I think during the first lecture in this chapter. So you know that a polar Protic solvent is one that's polar, of course, but possesses the capabilities of hydrogen bonding oftentimes and stabilizing, or hydrogen bonding, sorry, which serves to help stabilize the leaving group, and they can also stabilize the carbocation. So you can see that since water, methanol, and ethanol are polar Protic solvents, that the relative rate, that the reaction can occur in these solvents, where if we have a polar aprotic solvent, that the reaction rates are just so low that it's going to be a useless reaction. Now, I'll be honest, I've been teaching this class for a long time. I don't remember ever asking my students a question, about, explain to me why a polar Protic solvent is going to be more beneficial to an SN1 or E1 reaction, and an SN1 or E1 reaction is not going to work in a polar aprotic solvent or simply an aprotic solvent like diethyl ether. I've never really asked that, so to speak, but you do have to understand the why. Okay, why it happens. Why is a polar Protic solvent going to be the best solvent to do an SN1 or an E1 reaction in? And if we compare the two scenarios that we've looked at so far in this class, now this is going back, I think, either to the last lecture or the lecture before that. If we talked about when we talked about SN2 reactions, we said that a polar aprotic solvent, something like acetone or DMSO, dimethyl sulfoxide, or HMPA, which is hexamethyl phosphoramide, I said those reactions are the best for SN2 reactions, right? A polar aprotic solvent. And I said that the reason why is that they can stabilize a positive charge, but they can't stabilize a negative charge, right? They're very poor at stabilizing negative charges, which renders the nucleophile higher energy, right? So that's my nucleophile is going to be higher energy. Whereas when we're doing an SN1 or an E1 reaction, the reason the reaction is going to occur best in a polar Protic solvent is because it stabilizes what? The carbocation intermediate, right? This is the carbocation intermediate right here. And you can see it's much better stabilized in a polar Protic solvent compared to an aprotic solvent, where the activation energy is going to be much higher. That's really all it is. Okay. So if you're confused about polar, aprotic, all these different solvents, Mr. Dion, wow, this is crazy. Well, if you look at these two summaries here, it really covers everything that you need to know about Protic solvents, aprotic solvents, and which ones work best for a bimolecular reaction or a unimolecular reaction. Okay. Now, again, an organic chemistry student needs to familiarize herself or himself with some solvents. And we've gone over solvents a few times in this class, so you should be aware of these kinds of solvents and other solvents that we have looked at in this class. So I don't just cover solvents for the fun of it. They're very important in organic chemistry. Well, let's talk more about the substrate, right? We've talked about leaving groups quite a bit in this class. Okay, we talked about what constitutes a good leaving group. Right? It's going to be a weak base or the conjugate base of a strong acid. So that explains why iodide is going to be a better leaving group than bromide and chloride. Okay. All right. Well, if the rate determining step for the unimolecular reactions in SN1 or an E1 is the formation of the carbocation, and of course you form a halide, then it means that the more stable the halide, the faster the ionization. So that means if we have a tertiary alkyl iodide, it's going to react faster than a tertiary alkyl chloride, simply because iodide is a better leaving group than chloride. What about the substrate itself? What about the carbocation that's formed? Well, if you were to just say to me, you know what, Mr. Dion, what you've taught me so far is that a tertiary carbocation is the most stable, and that's why an SN1 or an E1 reaction is going to occur with a tertiary or a tertiary alkyl halide versus a secondary or primary. I'd say absolutely, absolutely. You're 100% correct, and that's covered in these two bullet points right here. However, besides a tertiary alkyl halide, okay, which would produce a tertiary carbocation, we can also do SN1 and E1 reactions using benzylic and allylic halides. Okay, now they're going to undergo solvolysis because they don't produce tertiary carbocations, but they produce stable carbocations. Now, what's the difference, right? This carbocation is stabilized by hyperconjugation, right? The different alkyl groups. Here, there's 3 alkyl groups around the carbocation, and they stabilize it by hyperconjugation. If you just look at this one here, if I was to just tell you, or just asked you 2 lectures ago and say, what kind of carbocation is that? You might say, well, it's primary. It looks like it's primary, but it is primary, but it's benzylic. Okay, and we know that we could draw 3 more resonance structures for this carbocation, right? This goes all the way back to chapter 2, right? You could start by drawing a curved arrow like this and practice drawing all of the different resonance contributors. The same thing with the allylic carbocation, right? You should be able to draw the resonance arrow like that. There's not a lot of space here, but you see that that positive charge is delocalized over those 2 carbons. And so based on resonance stability, you have to be aware of the fact that not only tertiary alkyl halides can undergo SN1 and E1 reactions, but also benzylic and allylic halides can undergo the same kind of reaction. And instead of hyperconjugation stabilizing the carbocation, it is resonance that stabilizes the carbocation. Give me a thumbs up if you follow me on that concept. Just stabilization of the carbocation based on resonance rather than hyperconjugation. Yeah, thanks. That's something that's going to come up more and more, throughout the course. But of course, you need to know it in this chapter. Otherwise, I wouldn't be bringing it up, right? So if we look at a reaction here, it says, be able to judge whether or not a given alkyl halide will undergo solvolysis. What does that mean? It means if I was to just present you with this reaction right here, say you take this alkyl halide, okay, and then you put it in water. That's all you do. Just throw that alkyl halide in some water. Does anything happen? You've got to be able to answer that question as an organic chemist. And you might say, well, Mr. Dion, you misspoke. That's not just an alkyl halide, okay? That's a benzylic alkyl halide, okay? So you kind of spice it up there a little bit, right? It's not just benzylic. Not just an alkyl halide. It's a benzylic alkyl halide. And we know that when you lose this leaving group, okay, if you were to lose that, now I'm just drawing it here to help us out, you end up with this intermediate, right, which is resonance stabilized. And that's why this molecule can undergo a solvolysis reaction to give you the SN1 and E1 products. Okay, so again, kind of thing that you have to be on the lookout for as an organic chemist. Okay, let's talk about the regioselectivity of an SN1, of an E1 reaction. Now, when we looked at E2 reactions, we saw that we could end up with different regioisomers depending on the type of base and the type of alkyl halide that we were using. But it's possible for an E1 elimination to also yield more than one regioisomer. So if we take this tertiary alkyl halide that's shown right here, nothing fancy, just a regular old tertiary alkyl halide, you know that you could lose that leaving group to form this carbocation intermediate. Now, what's that carbocation going to do? Well, I have beta protons here, and if I abstracted one of those, I would end up with this product. I also have beta protons here. If I abstracted one of those, I'd end up with this product. And then I could also get the substitution product, right, after the nucleophilic attack and proton transfer. But in E1 reactions, we're always going to get the most stable alkene as the major product. Okay, so the most stable alkene is going to be the one that's the most substituted, right? This is a tri-substituted alkene. This is only a di-substituted alkene. So this is something that you've also got to be aware of. In the E1 reaction, that the most substituted alkene is going to be the major product. Now, what's cool about these reactions is that they're regioselective. Just as an organic chemist, I find it interesting. I think it's cool when a reaction is selective at all. But the problem with these reactions is that you can't control the regioselectivity just by going to the cupboard and choosing a base, right? Like we could with an E2. So in our book, I think he says something kind of funny in there, like, you know, you can't control the regioselectivity of an E1 reaction. So you might be asking, what the heck's the point of it? Well, there are plenty of examples where an E1 reaction is going to be very helpful for us. And I'll show you some examples of that later on. Anyhow, what about the stereoselectivity? If you can form a bunch of different alkene stereoisomers, like you can in this one here, of course, you can always practice drawing your curved arrows, show your loss of leaving group to form the tertiary carbocation like this, okay? Then water can come in as a nucleophile, or we could abstract a proton. Now, again, we got two types of protons, two types of beta protons. We have this one here that would produce this product, but we have these ones here which could produce either one of these. Now, again, the most substituted alkene is going to be the major product, but I have two different tri-substituted alkenes. So which one is going to be major? Well, it's going to be the one that's going to be least sterically hindered, which would be this guy here. If you're wondering why is that least sterically hindered, well, you can see that the methyl group here is trans to this ethyl group, whereas here the methyl group is on the same side. So it's just going to be less sterically hindered. Now, you might think, oh, it's not a big difference in energy, and it probably isn't, but we can still predict which one or which product is going to be the major product, okay? We're still going to end up with a soup, aren't we? We're still going to end up with 4 different products. Now, I worked as a bench chemist most of my adult life, and I can tell you that reactions where you produce 4 different products aren't very useful, I would say, but there could be situations where it might be your only choice. And we're going to talk about, again, SN1 reactions that are going to be very useful in synthesis later on. If you're an astute student, which I know you all are, you might be questioning, now hold on, Mr. Dion, all you've been talking about is stuff like this where there's no chiral center. What if you got a chiral center? What's going to happen then? Well, that would be a really good question for my students to ask. So here we have a tertiary alkyl halide, but not only is it tertiary, it's chiral, right? So this is a tertiary alkyl halide that's chiral. Now, you know that the first step is the loss of leaving group, and you end up with a carbocation. This carbon is sp2 hybridized. If you were to say to me, you know, Mr. Dion, from everything I've learned from my first semester of general chemistry, I know that an sp2 hybridized carbon is trigonal planar, right? That's why they've drawn it like this. And then you'd say, well, if that is trigonal planar, right, you can say, and I'm going to put it in quotations and hear me out, okay? If that is trigonal planar, that means planar, my friend, means flat like a pancake. That means that the nucleophile can come attack that carbocation from either side. It can attack it from over here, or it could attack it from this side. Why the hell would it discriminate if it's flat? Right? So that means I'm going to get inversion of configuration, right, where it flips like the umbrella in the wind, so to speak. And I'm also going to end up with retention of configuration, where the configuration remains the same. Okay? Well, you remember that then the SN2 reaction, you only get the backside attack, and you only get the inverted product. Well, here's the truth about the stereoselectivity of these kinds of reactions. And it's not even in my slides, so I must not think it's of great importance. Otherwise, I would have harped on it a little bit more with you guys. But let me tell you the truth about these kind of reactions is that for this class, if you were to, you know, do this kind of reaction for me personally, and you said, you're going to get a racemic mixture, Mr. Dion, you're going to get a 50-50 mixture because, come on, that's flat. The nucleophile could attack from either side. I would give you 100%. I would say you're absolutely correct. If you look at our book, and I'm sure you all read the textbook before coming to class today, you probably noticed that the book says, well, you actually end up with a little more inverted product than you do where you have the retention of configuration. Okay, so he said you actually end up with a little more backside attack. But you know what? It's not that it's not here nor there. It's not that it's completely unimportant, but I'm never going to ask you about that. And my students love to know when there's something I'm not going to ask them about, and rightfully so, because there's so much material in organic chemistry. So you can just assume that you're basically going to end up with a 50-50 mixture or a racemic mixture. But if you read what it says in the book, you get a little bit more of the inverted product. But again, I'm not going to quiz you on that, really. All right, well, let's take a look at some reactions. This is a great kind of reaction for me to ask on a quiz. Nothing fancy. It says draw all the expected products for each of the following solvolysis reactions. So that tells us this is going to be SN1, right? We're talking about SN1 and E1 reactions if it's a solvolysis reaction. It doesn't ask us to draw the first step of the reaction, but I'm going to do it. This is the land of the free. All right, so we're going to end up with this carbocation right here. Now, what the hell can that carbocation do? Well, it could be attacked by water as a nucleophile, right? Why not? And if you're the kind of person that likes to draw the curved arrows for everything, you would draw the nucleophilic attack, which would produce an oxonium. Then you would do a proton transfer, and you'd end up with this as a substitution product. So you'd end up with this guy right here, okay? Now, that's not going to be the major product because we said the E1 product is going to be the major product. Well, what are the possible beta protons? I have beta protons here. If I eliminated one of those, I'd end up with this exocyclic alkene like this. And if I was to rip off this beta proton, then I'm going to end up with this as my product. Could anybody tell me which one of these would be the major product? And it's not a trick question. Just by color. Red, blue, or green? Yeah, thanks, Skylar. This is going to be the major product. Why? Because this is the most substituted alkene. It's not meant to be, you know, a mind-boggling problem or anything like that. It's just a good old solvolysis reaction. But you can see how you got to apply not only your logic skills, your organic chemistry, just logic skills, but you also have to apply a little bit of memorization that the E1 is going to be the major product. Okay, let's take a look at the next one. Again, Mr. Dion just loves to draw as many curved arrows as he can. So let's see here. The first step is going to be the loss of a leaving group. Now notice this is a chiral center, isn't it? Got a beautiful chiral center there. Well, what are we going to produce after the loss of leaving group? Let's draw it. We're going to end up with something that looks like this. So we're going to have this group coming off here like this. But now, right, this is sp2 hybridized, right? So that's going to be trigonal planar. That means the methanol, which is going to behave as a nucleophile, can attack from either face of the molecule. Now, I'm going to see if I have room to draw the product. So that means you're going to end up with this product. And just let me do this as quickly as I can. We're going to have the methyl group down in the methoxy group, but the methyl group coming up, and then you're also going to end up with the enantiomer. Now, in our book, I don't know if he draws both of these out explicitly. And you can do that if you want, and if you don't want to, that's fine too. All right. So this would be, and you would just write that this is a racemic mixture. So that's fine. And then we're also going to get the E1 products. Again, we've got beta hydrogens here that would produce by the E1 mechanism. E1 mechanism that would give us this guy right here. Cha-cha, like that. And then you could also abstract this beta proton here, which is also an E1 reaction, of course, which would give you this one here. Come on. There we go, like that. Could anybody tell me which one of these would be the major product? And again, it's not a trick question. I hate trick questions. Yeah. Thanks, Byron. Absolutely. You're all right. Lauren, everybody is correct. Okay. There we go. Everybody is 100% correct. I like the way my students think, right? Just using their logic skills, right? When you're solving some problems that deal with organic chemistry. What else is I going to say about this? Oh, I know something I wanted to share with you quickly. You guys remember what conjugation is? Remember when you alternate double, single, double, single, double, single, right? That's what a conjugated system is. And the more conjugated a system is, the more stable it is. Well, look at both of these products. Did you notice that both of these are conjugated alkenes? Right? Notice the double bond is conjugated to the ring, right? It goes double, single, double, single, double, right? They alternate like that. And the same thing is true for the one that's in green. So that's another reason why these are so stable. All right, let's move on from there. Let me check something here quickly. We're going to move on. Section 7.10. I can cover that pretty quickly because we're skipping it. All right. So we're going to skip section 7.10. I'm not going to ask you anything about that. But 7.11 is probably the most important section in this entire chapter. It's what I would say is the most important section. Now, that's really risky for an instructor to say that because I don't want my students to say, all I did was study section 7.11. You know, you said it was the most important. Well, I'd say that this is where you're going to apply everything that you've learned in chapter 7 the most. Right? You're going to have to look at any kind of substrate, any kind of nucleophile, any kind of base, any kind of solvent, and say, what the hell is going to happen? Pardon my language, right? You just have to be able to look at it and say, what's most reasonable? So let's just kind of go through it together. I try to summarize things the best I can in my slides. It says, you know, by this point, you understand that what's going to affect the reaction? The substrate, your alkyl halide, your nucleophile, your base, and your solvent, right? All of these things are things that you're going to have to evaluate. You should have also realized that in a lot of cases, you just end up with a mixture, right? You end up with a soup, okay? So in this case, we're taking a secondary alkyl halide. It's chiral. We're getting some E2 products from the elimination, and we're also ending up with some SN2 product and that results by an inversion of configuration. So all kinds of different things are going on, things that you've got to be aware of. Okay. Now, if you're wondering, hey, do you have this summarized in a table somewhere? Well, that's where we're getting. Okay. I do have this summarized in a table that's found in your textbook. Now, sometimes you only get one mechanism. Right here, we have a tertiary alkyl halide, and we have a strong base. Okay. In that case, we're only going to get one product. Now, in order for you to understand how to transform the alkyl halide into a compound, you've got to be able to predict all the products as well as major and minor products. Might seem daunting at first, but hopefully there's something that you've all realized with organic chemistry, and that is repetition will help cement or help these concepts to crystallize in your mind and help you to really understand what's going on. Okay, so there's always a kind of a stepwise approach you can take to solving problems in organic chemistry. It's one of the things I really love about it. Here's a three-step analysis that you can do. It's just 3 steps, and they're all this, right? They're all number 1. So 1, 2, and 3. First, you look at your reagent. That's where I like to start. It's because you know, it's just what I like to do. I like to look at the reagent first and say, hey, is this a good nucleophile? Is this a good base? What kind of base is it? Is it strong, weak, that kind of thing? Then I look at the substrate. Okay, is it primary, secondary, tertiary, benzylic, allylic? What the heck's going to happen with that? And then I consider, you know, what's the regiochemistry going to be? What's the stereochemistry going to be? And then I predict all of the products. Well, in order for us to be able to decipher or to discern what the function of the reagent would be, it's really helpful for us to have a table. Okay, now this is a table that, again, comes from our textbook. And I think having it in tabular form, it really helps you memorize it too. So I would say that you need to memorize this table. Memorize. Now, if you're thinking, okay, Mr. Dan, all I have to do is memorize all this gobbledygook, SN1 and this, you know, I have to put all this junk together. Well, yes, but again, it's all logical. Okay, it is logical. I have, you know, It is, okay? And it's going to become more and more logical as we look at many examples. So if we have a strong base that's a weak nucleophile, we're going to favor an E2 reaction. What are strong bases that are poor nucleophiles? Things like sodium hydride, right? A hydride ion, H minus, like that. It's a good base, but it's a bad nucleophile. And so it's going to preferentially do elimination reactions. Now, you might be wondering, what the heck is a DBN and a DBU? We'll talk about that in a second. But again, those are bases that are strong, but they're very bad nucleophiles, and there's good reason for that. Next, to favor an SN2 or an E2 reaction, we'll need a strong base that's also a strong nucleophile. Examples of those would be hydroxides or alkoxides. So notice they all have something in common. They all have an oxygen with a negative charge. Right? It makes sense that they're going to be strong bases. You're like, of course I know this is a strong base. Of course I know these are strong bases. They're the conjugate bases of weak acids. Well, I know that those are going to be strong. And of course I know they're going to be strong nucleophiles because they have negative charges. Right? Now, if we move over to weak bases that are strong nucleophiles, well, how do you know that they're strong nucleophiles? Well, most of them have a negative charge, and the ones that don't have sulfur as the nucleophilic atom, and sulfur is much more polarizable than oxygen. And I explained polarizability earlier on in this chapter. And so these are weak bases because they are the conjugate bases of stronger acids, all right? And they're also good nucleophiles. So those are going to favor SN1 and SN2 reactions. And then finally, to favor an SN1 or an E1, well, we spent a lot of time talking about those this morning. Those are going to be weak bases and weak nucleophiles, things like water and alcohols, methanol, ethanol, isopropanol, whatever. All right. To go over that DBU, DBN thing, I'm never going to ask you the structure or to draw the structure of DBU or DBN. So DBU is diazobicycloandecene, and then DBN, you see it's got this big name here, and you can notice that I even left some things out in their names. When I was a graduate student, I used DBU for a whole pile of reactions. In fact, I basically wrote a whole chapter in my thesis about reactions that use DBU. Now, we know that nitrogen is a basic atom oftentimes, and it is in DBU and DBN. And when they accept a proton, whether it be DBU or DBN, we end up with a resonance stabilized cation. So that shows you why they're good bases. Okay, but the reason they're non-nucleophilic is just because they're so damn big. Okay, they're so sterically hindered that they're not going to attack anything. So again, I won't ask you to draw DBN. I'm not going to ask you to draw DBU, but I need you to know DBN and DBU are non-nucleophilic bases, and they're strong bases, and I need you to be able to recognize them. But if all you have to do is see the six-membered ring, which is in common with them, and you'll know that you're dealing with either one of them. And to be honest, I don't even know if their structures come up again in our textbook. The DBU and DBN, the acronyms come up all the time in organic chemistry, but I don't even know if he ever shows the structure of these again in the book. Okay, it kind of goes over them pretty quickly. Well, here's another figure that's extremely important for you to have memorized. I can't remember which figure this is. It's 7 point something, but anyhow, this one is in our textbook, and I've taught this class long enough to know that many of my students print this out, you know, and we'll go over it and over it and over it and over it. And I would say there probably is a good chunk of memorization at the beginning, but once the students start to understand the rationale, right? When you're home alone and you're solving problems that deal with substrates, nucleophiles, and bases, I don't want you to just think about this table. I want you to maybe think about the table at first, but then ask yourself, why? You know, does this make sense? Okay, so depending on whether our substrate is primary, secondary, or tertiary, if we have a strong base, strong nucleophile, what were those? Things like sodium hydride, DBU, DBN, right? Those are all going to give you E2 reactions because they're good bases, right, for elimination, but they're not going to be good nucleophiles, so you're not going to get any substitution. If we have a strong base that's a strong nucleophile, what were those? Those were things like hydroxide or an alkoxide, like methoxide, ethoxide. Well, those are really strong bases. They're really strong nucleophiles. If you have a primary substrate, the carbon is not very hindered, and so substitution is going to predominate. But once you get to a secondary, it gets more hindered. So elimination will predominate. And then once you get to tertiary, you're going to get no substitution, only elimination. If you have a weak base, strong nucleophile, these are things like chloride, bromide, and this isn't going to be an exhaustive list, right? The hydrosulfide, what else? H2S, a thiol, things like that, okay? Those are not going to give you any elimination reactions or any elimination products because they're weak bases. However, they will do substitution reactions. And then finally, if you have a weak base, weak nucleophile, so those are again things like water or an alcohol like methanol or ethanol, and then it gets, only one possibility. You've got to have a tertiary substrate, and you're only going to get SN1 and E1 products, and the E1 is going to be the dominant product. Now, if you're wondering, are there any exceptions to this table? And you're probably hoping that there aren't. There are some exceptions to this table, but I didn't have anything in my notes. So we're not going to focus on the exceptions right now, okay? Not going to linger on exceptions. So I'm going to skip the next few slides because they just kind of go over the decision tree, or basically the decisions that you need to make when you're analyzing your substrate and your reagent. So those are covered in these slides here. So whether you're dealing with an SN2 or an E2 reaction or an SN1 reaction or an E1 reaction, I'm not going to go over that in detail because it's covered in here. It doesn't take you a long time to read. The best thing to do is to start looking at reactions, okay? Here we have a secondary alkyl halide, right? And we're treating it with a strong nucleophile, strong base, right? So what's going to predominate here? Well, if you go back to this chart, all the way back here, you have a secondary alkyl halide and you have a strong base, strong nucleophile. So that means that E2 and SN2 mechanisms are going to predominate, and the E2 is going to be the major. But when you look at that substrate, you say, well, jeepers, how many types of beta protons do I have? Right? Not only do I have these beta protons here, but I also have these beta protons here, and I could draw one is going up and one is coming down like this. Okay? So we can get, again, both the SN2 and the E2 products, but the E2 is going to predominate. The reason why is because secondary substrates are hindered. So backside attack is going to be more difficult in that case. Well, you can start by drawing the SN2 product. That might be the easiest one. You would just draw, the product of the nucleophilic attack. So you could practice drawing your curved arrows. We get a nucleophilic attack followed by a loss of leaving group. We do the inversion of configuration. There you go. That's our SN2 product. But that's not going to be the major product, is it? Right? The elimination products are going to be the major products. So if I have my base pulling off HA or HB, I'm going to end up with these elimination products here. And if I have it pulling off one of the HC protons, I'm going to end up with this elimination product. Now, which one of these is going to be the major? Both of these in the green box, both are di-substituted. But then you still have a choice to make. If I call this one, the one from HA or the one from HB, could anybody tell me which one would be the major product? The one that resulted from the elimination of HA or HB? And it's not a trick. Skylar, I thought you were laughing for a second there, right? I thought you were all laughing. Oh, I'm kidding. Anyhow, you're all correct. Okay, all of my students that are saying HA, you're all 100% correct. You're getting it. You're understanding that this one's going to be the less sterically hindered, right? Because the methyl group and the cyclohexyl group are trans to each other. Here, they're on the same side of the molecule. It's going to be much more sterically hindered. And so this will be your major product, like that. Oops. There we go. So most stable alkene, we've covered all that. So with all that in mind, let's take a look at a practice problem. I think this might be one of the ones I went over on the YouTube videos, but whatever. Let's take a look at it here. Again, let's do our decision making here. For A, we've got a secondary. So this is A. We get a secondary alkyl halide. Okay, it's not benzylic. It's not allylic. Okay, good. We've got a polar aprotic solvent. So polar aprotic solvent, which is going to favor a bimolecular mechanism. And then what else do we have? We have chloride, which is a strong nucleophile and a weak base. A strong nucleophile, weak base. So in this case, we're not going to get any elimination. If we go back, and forgive me for scrolling around here so much, but if we go back here, we have secondary substrate, we have weak base, weak nucleophile, we're only going to get SN2. And if you're like, well, that's only one product. Yeah, only one product in this case, which makes it kind of, you know, don't have to draw as many products, which is kind of nice. So let's see here, like that. And we're going to have an inversion of the stereocenter like that. Give me a thumbs up if you follow me on that one. Because if you do, that means you understand the concept of what's going on. Right? Just taking a look at the substrate, the reagent, the solvent. Excellent. Thanks, you guys. That's great. That's good. Now, I'm not asking you to, can you answer everything right now? Are you the world's foremost expert in organic chemistry? Absolutely. You don't have to be that. I just want you to be able to understand what's going on. Let's take a look at the next one. We've got a tertiary alkyl halide. So let's write that down. So this is B. Come on. In B, we've got a tertiary alkyl halide. All right. What else do we have? We have a strong base, strong nucleophile. Let's go back. Where are we here? Sorry again about rifling around here so much. So we have a tertiary alkyl halide, strong base, strong nucleophile. We're only going to get an E2 mechanism occurring. So let's go back and look to see if there's more than one type of beta proton in our molecule. And yeah, there is. All right, we have these beta protons here. If we were to pull off one of those, we'd end up with this product. We also have this beta proton here, or these kind. If we were to pull off one of those, we'd end up with this as our product. And this is going to be our major product because it's more substituted. Also, I should have added that the strong base is unhindered. Okay, so that's the kind of approach that we want to take. If you take a look at C, you notice that you have a strong base, but it's a hindered base. And so in that case, it's going to favor the E2 product. So if we go over here, we have a tertiary alkyl halide, and we have a strong base. So we have a strong base, but it is not a good nucleophile because it's too hindered. We're only going to get E2 in that case. Okay, so there we go. When we go back here, we end up with, come on, we're going to end up with this as being our major product. Since, again, the base is hindered, so this will be our major product. And then we'll also get some of the minor product as well, which would be this guy here. This will be the minor product. All right, well, let's move on from there and talk about section 7.12, which deals with other substrates. So besides alkyl halides, you might be wondering, is there anything else that could behave as a leaving group? And the answer is absolutely. So besides halides, so we've looked at, you know, alkyl chlorides, alkyl bromides, alkyl iodides. There are options for other good leaving groups, and those would be what are called alkyl sulfonates. So here we have 3 different types of sulfonates. You need to be aware of these. And probably what you're going to see the most in this class will be their acronyms. So this one is called the mesylate group. So that stands for methane, or it's a shortened version of methane sulfonyl. We just abbreviate it as OMS, the O mesylate group. The next one is a tosylate. Tosylate is a shortened version of toluene sulfonyl. There we go. So that's the tosylate is OTS. And then the last one is a triflate, which stands for trifluoromethane sulfonyl, which we abbreviate OTF. Son of a gun, I didn't mean to do that. And if you're wondering, you know, Mr. Dion, I am tired. What are all these things about, Mr. Dion? All these are about is nothing more than this. If you have a mesylate, a tosylate, or a triflate, these are all excellent leaving groups. Okay, they're just good leaving groups, just like an iodide, a bromide, or a chloride. So you can treat them in the exact same way. If you're wondering, if you've got an inquiring mind and you're wondering what makes these guys such great leaving groups, well, it means that they must be, excuse me, when the after the substitution reaction occurs, that the leaving group must be the conjugate base of a very strong acid, right? It must be a really weak base. Okay. The reason that these are really weak bases is because they're so stabilized. You can draw these resonance structures for them here. And if you look at the pKa's of their acids, of their conjugate acids of the leaving groups, we have methane sulfonic acid, para-toluene sulfonic acid, and trifluoromethane sulfonic acid. Look at the pKa's of these guys, okay? These ones are only -2 and -3, but look at the pKa of this one. -14, that's stronger than hydroiodic acid. That's a very strong acid, my friend. Now you might be wondering, hey, if this is so awesome, if this would make such a great leaving group, the triflate, if this makes such a dandy leaving group, why don't we just use that in everything? You know, why don't we always use that? Well, there's good reasons why we don't always use a triflate. The reason why you're going to see this one occur the most, or the tosylate, which comes from toluene sulfonic acid. So you're going to see the tosylate the most, I would say, in this book. You're going to see the other ones too, but tosylate predominates. The reason why, in my opinion, is because toluene sulfonyl chloride, which is what you would use to make the tosylate, is a solid. So that's this guy here. So tosyl, which stands for, again, toluene sulfonyl. This is a solid at room temperature, and organic chemists love things that are solids at room temperature that they can just weigh out on a balance, right? Dealing with liquids there's always a little bit of pain associated with that. If you can weigh something out on a balance and it's stable, boy, oh boy, that's going to be a lot easier to deal with. So tosyl chloride would be your starting material. And the way that you use a tosylate as a leaving group is that you've got to start with an alcohol. Okay, you take an alcohol, you treat it with tosyl chloride, you end up with this intermediate oxonium, and then pyridine comes in and acts as a base, and you end up with the alkyl tosylate. And again, this is the same thing as O or ROTS, right, which is shown here. So you're going to see it mostly the acronym. Now, remember that this mechanism here that's occurring is happening on the oxygen, right? The oxygen is acting as the nucleophile in the first step. Now, they've left it out here. I'm not going to draw the whole thing. But that reaction is occurring on the oxygen. So there's no change to a chiral center. So if you want to take an alcohol and convert it into a good leaving group, all you do is you treat it with tosyl chloride, which is, again, this guy right here, TSCl, which is toluene sulfonyl chloride, and pyridine. So you mix the two together. Pyridine, we either use PY or sometimes we use PYR. That's what I'm used to. Is both of those acronyms are perfectly fine. So you end up with retention of configuration when you take the alcohol and you convert it to a tosylate. And now you've got a good leaving group. So again, you can imagine, or you can consider the tosylate to be reactive in the exact same way you would an alkyl halide, right? If you take a primary tosylate, you treat it with strong nucleophile, strong base, what are you going to get? Mostly SN2, a little bit of E2. If you take a secondary tosylate, do the same thing, strong base, strong nucleophile. I told you that since this is sterically hindered, you're going to get mostly E2 with a little bit of SN2. So the take-home message is, if you want me to summarize this really quickly for you, the behavior of a tosylate is the exact same as an alkyl, iodide, bromide, or chloride. Okay? They can be synthesized from an alcohol. You need to know that reaction. Okay? You need to know what a mesylate, tosylate, and triflate is. And the one that's going to come up the most, I'd say, is the tosylate, followed by the mesylate second, and the triflate will come up the least. Okay, that's my opinion. Okay, not my opinion, but that's my opinion after reading this textbook. So let's give a try here to a practice problem. It says predict the major and minor products for these reactions. The first step is we're taking this secondary alcohol and we're treating it with tosyl chloride and pyridine. This first step is going to occur with retention of configuration, right? We're not going to invert that stereocenter, but now instead of OH, we're going to have OTS, the tosylate. Now we've got a dandy leaving group on a secondary So we get a secondary leaving group. It's not a secondary alkyl halide, it's a secondary tosylate in this case. And next we're treating it with a strong base that is going to be a crappy nucleophile because it's so sterically hindered. And so we're only going to get the E2 products, right? We're only going to get E2 products occurring. Well, we get two kinds of beta protons. We've got this kind here, which is going to result in this product. And then we've also got this one here, which is going to result in this product. Could anybody tell me which one of these would be major? Would it be the one in black or the one in green? Remember, this is a really hindered base. Yeah, it's going to be, the green one is going to be major, and that's because base is hindered. Like that. Okay, we'll do the next one. Next one, we're going to take this alcohol, we're going to convert it into a tosylate. So we have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 carbons. Then we're going to have the tosylate like this. Next, we're treating it with strong nucleophile, strong base. It's a primary alkyl halide. The major product is going to be from the SN1. So if it undergoes an SN1 reaction, we're going to end up with this. So this will be the major product. And then we're also going to end up with a little bit of elimination, which will give us, we'll say E1. And did I say SN1 when I meant SN2? Sorry about that. Mr. Dion needs to stay on his toes here. And this is not an E1, this is an E2 mechanism. Just so much content to cover here. 1, 2, 3, 4, 6, like that. And that is going to be our minor product, the product from elimination. All right, section 7.12 deals with alcohols. What the heck can you do with an alcohol? Well, you can take an alcohol, a primary alcohol, treat it with HBr, and you end up with a primary alkyl bromide. Now, how would that work exactly? Well, we need to do this reaction in acidic conditions because an alcohol, a hydroxyl, is not a good leaving group, right? If you can't just lose this as a leaving group, that's the conjugate base of water, which is a weak acid. So if we convert it to an oxonium like this, then we have water as the leaving group. Water is the conjugate base of hydronium, which is a strong acid. So we simply do a proton transfer followed by a nucleophilic attack like this, and we end up substituting the hydroxyl for a bromide. So that is a reaction you need to be aware of. This one right here. Primary alcohol plus HBr gives you a primary alkyl bromide. You need to know this mechanism too. What if I have a tertiary alkyl halide and I try, or sorry, a tertiary alcohol and I try the same thing? Is that going to work? Well, it is going to work. You're going to end up making a tertiary alkyl bromide, but the mechanism is different. It's going to be an SN1 mechanism, right? The first step is the proton transfer. The next is the loss of leaving group. But when I lose that leaving group, I end up with a carbocation that is tertiary, and then I have a nucleophilic attack occurring at the end. Again, you've got to have strongly acidic conditions in order for this reaction to occur, in order to convert the alcohol into a good leaving group. Okay, but strongly acidic conditions are Protic conditions, aren't they? Right? Because if you have it in HBr, right, this is a polar Protic solvent, if you will. Okay, there we go. What else? This is another reaction that's going to come up a lot, and that is taking a tertiary alcohol and treating it with concentrated sulfuric acid, okay, to produce an alkene. Now, again, these are also Protic conditions, which is going to favor an E1 reaction. The first step is going to be the proton transfer to produce a good leaving group. The leaving group leaves, and then we get an E1 reaction occurring to produce an alkene. This reaction comes up a lot in organic chemistry. Now here, in this one that I have in the yellow box, there's only one possible alkene that you could get, or only one possible regioisomer. But when you do this reaction, you usually get the Zaitsev product, which is the more substituted alkene. It's going to be the more stable one, right? The more substituted alkene. So with that in mind, let's take a look at question 7.42. It says predict the major product for each of the following reactions. If I take this secondary alcohol, or sorry, tertiary alcohol, and I treat it with HBr, it's not asking us to draw a mechanism, but we could draw one out, couldn't we? The first step is going to be the proton transfer to form the oxonium, which has converted the alcohol into a good leaving group. We get the loss of our leaving group, which is going to form the tertiary carbocation, like that. And then in the last step, the bromide that was produced in the first step is going to come in as a nucleophile, and we're going to end up with this tertiary alkyl bromide, like that. The next one is treating it with concentrated sulfuric acid. Remember that the most abundant acid in sulfuric acid, which is dissolved in water, is going to be the hydronium ion because of the leveling effect. The first step is going to be the proton transfer to form a good leaving group. I don't know if I have time to draw all of this out, but you're going to end up forming the same intermediate you did in the first case. Okay, this is going to be our leaving group. You lose the leaving group, and then water is going to come in and act. The water is going to behave as a base in this case, and we're going to end up with the elimination product. So I just can't help it. I'll draw the carbocation, and then water is going to come in and behave as a base in this case, and it's going to abstract this proton to form mostly the Zaitsev product, the more substituted product. Here it's asking us to draw a plausible mechanism for these. I drew plausible mechanisms for the last two, and so I'm going to move on ahead to section 7.13. We don't have a lot of time, but the good news is that we've covered all of the material in the chapter, okay? All of the material has been covered. And the most important parts of 7.13, I would say, are covered on these first two slides. So let's go over them in detail and look at all the different transformations that we've seen in this chapter. If we take a primary alkyl halide, we treat it with a strong nucleophile, strong base, we're mostly going to get the SN2 reaction. We're mostly going to do a substitution. We just saw that if we take that primary alcohol and we treat it with HBr, we convert the alcohol to a good leaving group, then the bromide comes in and acts as a nucleophile. We also saw that you can take an alcohol, primary alcohol, you can treat it with tosyl chloride and pyridine to make a tosylate, which is a good leaving group. So it stands to reason that if you take that good leaving group and you attack it with a strong nucleophile, it's a primary leaving group, that you're going to end up with a substitution reaction. What else? We saw that if you take a primary alkyl halide and you treat it with a strong nucleophile that is a weak base, you're going to end up with an E2, a strong base, weak nucleophile. Sorry, I'm getting mixed up here. You're going to end up with an alkene. If you treat it with a strong nucleophile, strong base, like a methoxide or an ethoxide, you're going to do an SN2 reaction to make an ether. If you treat it with a hydrosulfide, you can make a thiol, right? And if you're wondering, like, how the heck are these happening, right? This is just a hydrosulfide. It's a polyatomic ion that you should know. Since General Chemistry 1, we saw it in the table, the first table that we looked at today. The next one is an acetate. And you take the acetate ion. So the acetate is a very abundant ion in chemistry. So that's this ion here. That can also act as a nucleophile. You get loss of leaving group to get an ester in that case. And the last one is a cyanide, which can function as a nucleophile. Cyanide is another polyatomic ion that you should be aware of, right? Cyanide can function as a nucleophile, and we end up with a nitrile in that case. All right, so all these different nucleophiles, whether it's, an alkoxide, a sulfhydryl, or a hydrosulfide, an acetate, a cyanide, you get all of these different SN2 reactions. You get these E2 reactions here. And then we looked at some other substitution reactions over there. A tertiary alkyl halide, what can you do with this? Well, there's a lot of repetition on this one. If we treat it with a strong base, strong nucleophile, we're mostly going to get the Zaitsev product. We're going to get some of the Hoffman product in that case. Keep in mind this is a tertiary alkyl halide. If we treat it with a hindered base, we're only going to produce the Hoffman product. We would produce a little bit of the Zaitsev product as well. You see the exact same reactions for the tosylate. Tosylate and this are analogous. That's why all these arrows, right, are just mirror images, okay? Because the tosylate is going to react the same way an alkyl, tertiary alkyl halide would. Here we have the alcohol. If we treat that with sulfuric acid, we mostly get the Zaitsev product. It's the last reaction that we looked at in this chapter. We said if you take the alcohol and you treat it with HBr, it's an SN1 mechanism, but you get a substitution. And what else? If you take the alcohol and you treat it with tosyl chloride and pyridine, you make the tosylate, and that never changes. So that covers all of the content in chapter 7. And so what you're going to want to do is you're going to want to be able to, or try to, apply all of those different reactions to making compounds. Okay, so we don't have any time to cover the rest of these questions, but of course, as always, these questions are in your textbook, and I showed you how to access the solutions manual in case you didn't know how to do that, which gives you a step-by-step solution for every problem in the book. All right.